Hello everyone. So welcome to the second part of this discussion about the sum of squares hierarchy for the independent set in a graph. And all right, so the sum of squares is this powerful framework for designing some semi-definite programs for us. It's sort of indexed by the level, the degree, right? So you can have degree increasing degrees, right? And all right, so our main motivation for looking at the sum of squares for an independent set is that it's able, at least in principle, to recover to compute the independence number of a graph. But we may need a level that's very high, right? So contrary to the sort LP that we do not know whether it gives a tight value, for the sum of squares hierarchy, the upside is that we know that for a sufficiently large level, it does give the correct value. Of course, at that sufficient large level, we are essentially doing brute force. But you have a hierarchy, natural hierarchy, and one would expect that potentially it gets tighter and tighter. Possibly, in some cases, it doesn't. Here we have a very specific family of graphs. We don't know, right? We don't know the correct value, but it's very interesting that at least we have a proven guarantee that eventually sum of squares does get the correct value, right? So yeah, that was our motivation. And recall that in the sum of squares hierarchy, we think that we have formal variables. And here we have those x1 all the way to xn. They are Boolean variables. They are sort of indicators saying whether vertex I belongs to an independent set or not in our solution. And if we are all powerful, you'd like to ask for a true expectation operator where the distribution of this expectation operator is supported on maximum independent sets. But that's too much to ask, but it's a good analogy to keep in mind. So when you're designing algorithms for sum of squares, you're going to have limited information. The only thing that you can really evaluate are going to be low degree polynomials, but we tend to think that you're evaluating them on something that might resemble to some extent to a distribution, but it's not there. And typically, in designing algorithms for some squares, the hard part is to have this partial information, how to really round and deduce that you can really uh, get the correct value. So that's typically one tricky aspect of algorithms on sum of squares. But as we have seen, the hierarchy itself, at least for the independent set, is not very hard. For CSPs, it's also you're not going to cover here, but it's also not very difficult. But it's important to notice that the sum of square framework it gives a way of reasoning about polynomial optimization in more generality. So if you're interested, I encourage you to look it up. If you have a systems of polynomial equalities and inequalities, you can use this framework and get those relaxations. All right, so we have this. And one central element object for us was this notion of a pseudo expectation. Now, instead of being able to evaluate any polynomial, any function on the variables, you can only evaluate low degree polynomials up to degree d. And the running time to find the pseudo expectation is going to depend on the degree that we consider. And typically, if you consider a degree that's constant, we are running in polynomial time. Very good. And this pseudo expectation operator is not like the true expectation operator, unfortunately, right? So it's going to mimic some of the properties. So whenever you have two elements, I and j, that have an edge, the pseudo expectation can see that it should be zero. So that's something that you can explicitly enforce. You have Boolean linearity constraints and so on. But one thing that you cannot enforce is if you have something that's non-negative, that the pseudo expectation is going to be non-negative. The only thing that the pseudo expectation can enforce, and that's tremendously useful, is when you have a sum of squares, a function that's a sum of squares that's trivially non-negative, right? Then the pseudo expectation operator is going to be to give something that's greater or equal than zero, and that's very nice, right? Okay. And then we define more formally the pseudo expectation operator. Expectation of one, the pseudo expectation of one should be one. It should be a linear operator. So if you're summing scalar multiples of P and Q, you have bilinearity this. So you have this non-negativity on sum of squares. And all of this is very generic, right? To the sum of squares framework. So you're always going to have these properties. The fourth property is related to Booleanality. So you need to make two small fix of some typos. So here the degrees is at most d over 2 because you want the pseudo expectation to be well defined when we square. So the degrees does not exceed d. And here we have a variable, in the second one we have a variable p squared. So the total degree of this expression has to be smaller or equal than d. So this is d minus 2. Okay. Very good. So we have Booleanality. And the last constraint is that it needs to respect the fact that you are independent set. So whenever there is an edge and you potentially have another polynomial here, you should see 0. And in this case, it's enough to check for when P is a monomial, right? Because if you enforce this for all monomials, then by linearity, you're enforcing this for all polynomials. All right, so that's a side remark. And we sort of think that this is going to be equivalent to the pseudo expectation formulation that allows to think that you have something that resembles an expectation operator. When you're going to implement this, it's actually going to be a big PSD matrix, right? It's a very big PSD matrix. And I think we covered this a little bit fast, so let me go a little bit more slowly. On this, the idea is that we have a matrix indexed by subsets, right? Which indicate in this case the vertices, right? And the entries of this matrix, if you have an ST matrix, the intention is that this entry indexed by S and T here, as you said, is going to be pseudo expectation of the union, right? Precisely what you mentioned below here. So xi, it's the expectation of the union. And it's of the union because if a variable appears twice, it's squared, but it's a Boolean variable, it becomes itself, right? This is multilinear, so very good. And we need to enforce a bunch of consistency constraints, right? So whenever you have different sets, so I don't know, here you have S and T, and they have some union. But if you have other entry that happens, I don't know, some you consider some S prime and some T prime, and their unions somehow happens. So we have some S prime and some T prime, and then you consider the entry associated to them. So this is going to be the product of I belonging to S prime union T prime. And here you have the product of xi. And if this is going to be equal whenever the union of the two sets is the same, right? Because it represents the same expectation, right? So whenever you have that their unions are the same, we need to enforce this equality. So whenever we have this, very good. So and that's part of the SOS symmetry, right? So we really want the entries to represent evaluations of this pseudo expectation operator. And whenever the monomial that we see inside is the same, and several entries, they are going to have the same monomial, right? Once you factor that things should be multilinear, then we force the entries to be the same. And that's called SOS symmetry. So we have this very big matrix and potentially some groups of entries that they are set to have the same value because they represent the evaluation of the pseudo expectation on the same monomial. So very good. So that's what we have. And perhaps one of the key properties of this matrix is that its PSTness is equivalent to whenever you have a polynomial that's a sum of squares, it evaluates something that's non-negative, right? So these two conditions are equivalent. And one thing that we mentioned very briefly is that, okay, you have this moment matrix, and you can sort of represent a polynomial as a vector, right? So here notice that the sets that they represent monomials, right? So this would be the empty set, it should be the constant one. This would be x1 all the way to xn, and 1, 2 would be x1 times x2. So it's you're representing this moment matrix in what's called the monomial basis, right? And if you have a polynomial, you can write down its coefficients, right, in this monomial basis. So I don't know, variable x1, what is the coefficient, and so on and so forth. This is going to give us a vector, right? It's a vector with these many entries, right? And then if this vector happens to be, if you're considering something that's a p squared, then this is equivalent to looking at this quadratic form here. But the matrix is PSD, then we know that this is going to be greater or equal than 0, right? And in the more general case that you have a polynomial that's not necessarily a sum of squares, one thing that you can do is to express this as a matrix, right? You can say, because you're going to take the inner product with this MD. So we write which entries of MD we want to sum, and then we represent this as a matrix, right? And we see that this is going to give us linearity. The trace is linear, and whenever we have or I don't know what, a sum of polynomials here, we will be able to write as the sum of two matrices, and by the linearity of the trace, right? We can break into two evaluations. So this gives us linearity. If we think for a bit, this gives us linearity. And one very important thing that I did not mention is that in both cases, we would like to maximize, right? So in both cases, in the pseudo expectation language, you want to find a pseudo expectation subject to all the constraints from before, but you're also interested in maximizing the size of the independent set. So you want this quantity here to be maximized. And this is a linear function, right? Okay. This is going to, if you think from the perspective of the moment matrix, this is going to be a linear function on the entries of the moment matrix. So you're maximizing this because you are considering the maximum independent set. What we have discovered, discussed before, it's about feasibility, right? So very good. So that I hope makes things slightly clear from what we discussed before. But yeah, it seems that's a lot of definitions, but at the end of the day, it's a big PSD matrix with a lot of constraints, a bunch of linear constraints, and a global PSD constraint that allows to have this. And one of the nice things about sum of squares is that it allows us to reason about larger monomials, right? Linear programming, of course, you can have hierarchies and so on, but it feels a bit more natural to it. Sort of, in some sense, linearizes to some extent non-linear relations. But of course, you have a global PSD in this constraint. It's not very formal, but it allows to reason about polynomials in a way that we can efficiently compute, right? All right, very good. So we have these two views, and you're saying that sum of squares is very, very powerful, and let's try to understand why. So, and we have something that's called the completeness of this hierarchy, right? And it's an exact completeness. It means that at a sufficient high level of the hierarchy, so if the degree is 2 times the independence number of the graph, then the sum of squares, the value of the sum of squares hierarchy at level D converge is exactly alpha is the independence number of the graph. You need to go quite high to see this. For the Boolean cube, in our case, let's just take and think about our case. So our case, we have a graph, an exclusion graph on the Hamming scheme. So the vertices, they are in F2 to the n. So we have 2 to the n vertices, right? And for the regime that we care, the codes are going to be exponential size. So alpha for our exclusion graphs, they're going to be of the form 2 to the alpha n or something like this, right? When the distance is a constant, right? A constant fraction of n. So we have this guy that's that's as much. So it means that the degree that we need for sum of squares, it's going to be 2 times this, right? So it's a very, very large degree, right? So it's an extremely large degree for the convergence. And recall that somehow Del Sarte's LP is very close to degree 2 sum of squares, because the degree 2 sum of squares is theta, and then but Del Sarte LP is exactly theta prime. Theta prime is slightly strengthening, but the degree 4 already captures theta prime. So it's as if the degree that we need to go in sum of squares, at least we have a guarantee that it gets the correct value is this. And if you go to the degree 4, it already captures Del Sarte LP and possibly even strengthens it. So yeah, we currently can analyze something perhaps even below degree 4, and we would need to go all the way here. But yeah, we don't know. For all that we know, it could be the case that degree 2 SOS is already giving the correct value. At this point, we don't know. We would expect not, right? At least asymptotically, it might be giving something that's not too off. All right, so that's just some consideration for us in our case. Let me erase this part, and you can see that something very curious is happening. Let me make the description of the moment matrix even more explicit, right? So it's as if we have this matrix, the moment matrix, have n d over 2 times n d over 2. Very good. So we have this beast, and here we have some set index in the row, and then we have another set index in the column, and then you have this entry, and the matrix. This matrix is PSD, right? So we know that there are vectors. There's a vectorization for this matrix. So we know in particular that the entry, and let's call this MD. This entry MD S index by ST is equal to Vs inner product to Vt. So we know that there is a collection of vectors. Let V R and R belonging to n d over 2. So it's a PSD matrix. We know that there is a vectorization. So we can, so those are vectors, right? So sufficiently large array, and you can express in this way. And the way that we were expressing the constraints on this is that you're sort of saying, oh, M d st is equal to MD, that's the SOS symmetry, S prime T prime for all whenever the unions are the same, because that entry represents the same expectation, the same monomial, expectation of the same monomial. Very good. And we also need to respect the constraints of the independent set. So we have that M d st is going to be 0 whenever whenever the union is not an independent set in our graph. And of course, we need to satisfy the normalization of the empty set, that's corresponds to the expectation of 1. This is 1. So this corresponds to the expectation of 1 and call. All right. So we have this constraint. So that's like what you're enforced. So you're asking this MD to be PSD, and all those these constraints that I mentioned. That's the precise way of saying the constraints that we have. All right, and we have this vectorization, and let's try to play with this vectorization. So suppose that degree, we are under this assumption that degree is very large. So degree is 2 alpha g, 2 times alpha of the graph. And we are going to see that something very curious is happening now, because the claim is that the solution is already super rich, that you can take this solution at this level and then construct solutions to higher levels using the vectorization that we have at hand. Okay, and how you're going to do that? So suppose that you want to construct something at a larger level, a larger degree. We want to go to d prime, which is d plus something, some extra levels L. So L is some integer greater or equal than 1. And what we need to do, we need to give a new, so we need to say what is the moment matrix, right? MD prime out of this, right? And we need to give a vectorization. Okay, equivalent to, you can give a vectorization. And the vectorization that you are going to give, now you're going to be playing with larger sets. So you're going to, let's say, you're going to look at sets R prime belonging to n, choose the prime. And the idea is that, okay, so whenever the size of this is smaller or equal than d, then we know that this new vectorization, let's call v prime, of r prime, is going to be the same, because this is well defined, because we have enough degree on the other formulation. We can reuse the same vectorization. Reuse the vectors from degree d. All right, and now let's take a look at what happens when you need more. And when you need more, what we know, so this is the degree, and the degree we sort of ask to be, right, so this is the degree, so yeah, so it should be d over 2 here, d over 2, sorry, so this is d over 2, this indexation, this is d over 2. All right, yeah, this is good, because to be consistent with what we had before. So this is d, if it's greater than d over 2, we already know that, and what is d, right? We chose d, so that this is 2 alpha g divided by 2. So it cancels. So this is a set that's larger than the maximum dependent set, larger than alpha g. So in particular, we know that we cannot have an independent set there, right? We need to force everything related to the set to be 0, right? So the vectorization of this guy, Vr prime now, is going to be the 0 vector now. And why is this going to be okay, right? So it's as if we have our moment matrix here. So here we have 0, I don't know, we have several blocks, all the way to the degree d over 2, all the way here to the degree d over 2. So all the entries in this block, they remain the same, right? Ourselves more space. So all the entries here that remain the same because you are using the same vectorization to this part. And for subsequent parts, whenever there is a set that's too large, right, on one of the sides, the corresponding entry is going to be 0 because the vector in the vectorization is already the 0 vector. So you are going to be satisfying the constraints, the independent set constraints, right? So very good. That's going to be great. And this tells us that we can lift. So the SOS solution of degree D lifts to a solution of degree of SOS degree D prime. That's extremely good. And the value is the same, right? Because the value remains the sum of this part here. So some variables that we have in some small diagonal here, x1, xn, with the same value. With the same. And we know that the feasible set of the solutions is smaller. If you go to larger degree, the feasibility region is smaller, right? Because whenever you have a higher degree solution, you can always truncate, right? You can always look at this part, right? You can always truncate. So if you're showing that there is a solution at a lower level that lifts to a higher level, it's establishing that you cannot improve the value. So right, not improve the value because you have at least the solution from a lower level coming to a larger level. Okay, so typically we naively have this inequality. We always have this inequality that the value of this solution here is going to be tighter. It's always tighter because the feasible region, to say this is smaller because we have this inequality with the values. So SD. We have this nice inequality with the value. So this is the optimal value, and we somehow injected some solution here, right? So it forces the value to be the same, right? Because of this inequality. Well, the solution that we have forces the optimal value to be like this, at least. Value of SOS D. Then we have equality throughout. Because this is a maximization problem, and for the point, it's going to be at least that or larger, and then we are going to have equality. And that's very nice. It means that once SOS, and it makes a lot of sense, right? Because the SOS is trying to look at larger and larger regions, right? A larger and larger collection of vertices. And once it can see a collection that's about the size of the independent set, it cannot be fooled no longer, right? So if you try to see a larger region, SOS will know that set's not independent, right? And it's already powerful enough to fully see an independent set. right? Okay, and it means that you can lift. You can take once you go all the way to degree 2 times alpha, the independent set, the size of the independent set, it lifts all the way to n degree. And in particular, we can go to degree, lift all the way to 2 times the number of vertices in the graph, right? And if you go to a degree as high as this much, then rounding is going to be trivial. Rounding the SOS solution. Rounding is easy, and you can round and get exactly the same value. Rounding is easy, and obtain the same value of the relaxation in the same value. So you can get the same value of SOS 2V. All right, so we have this. You have this huge SOS solution, so that the rounding part is going to be easy. Let me leave this rounding part as an exercise. It's not very hard to round and get exactly the same value. So that's one way of showing that for the independent set, completeness is achieved at level at degree 2 times the independence number of the graph. All right, so I'm going to stop here. Thank you very much for your attention.